Thank you very much for being here. Good morning to you all. We embark this morning on the third morning of discussions and presentation from European projects in this European conference of presentation of the results from the road transport research projects. We will have a full morning discussing about human factors in transportation, and it's an honor to be in the big room for this. My name is Pasca. I'm a project advisor working in CINEA, which you very well know, so is the European Commission established executive agency dealing with climate, environment, and innovation projects. I will co-moderate this first workshop of 1.5 hours together with Magnus Granström from SAFER in Sweden. And we will be listening from 3 projects that I have had the pleasure and the honor to follow up during their implementation, and that I will continue to follow up in the next years, because the different projects that you will listen from are having different phases of implementation. We will discuss in the next 1.5 hours about human behavior, about system design, and about safety. But before that, I would like to ask you a first question to see whether you did wake up and whether the cocktail yesterday wasn't too, too heavy. So we all know that we have to use as much as possible the public transport or the active transport modes. However, most of us have still a personal car. So the question would be, how many of you have on your personal car an adaptive cruise control or lane keeping system? Please raise your hand if you have it. Okay, so some of us. Now the question is, how many of you use it regularly, be it on the highway or in the city? Okay, so possibly 50% adoptants of the system. We'll see now from the project if they give you arguments or to better understand the equipment in the car and the interest of using them. So for this, the objective now is to embark you on a short journey to show how human factors are influencing the efficiency, the safety, and also the sustainability of the transport. And for this, I will give the floor to Paolo Preto, who is coming from Austria. He's the principal researcher in the Institute for Human Factors and Driving Simulator at the Virtual Vehicle Research in Graz. Paolo, the floor is yours.
Thank you very much. Good morning, everyone. Let me first try out if that works. Yes, perfect. No, yes, okay. So I'm glad to have the pleasure to tell you finally today, after decades of research, what HEIDI stands for. It's Holistic and Adaptive Interface Design for Human Technology Interactions, obviously. What else? So this project involves 9 partners from 4 countries, including 4 research centers, 2 small, medium enterprise, and 3 large industries, including OEMs like BMW and Honda. And the budget is not too large, it's only 4 million euro, but we are very effective. And we are right now halfway to the project. 18 months. So indeed, we're going to have our midterm review in a couple of months from now. So that is also a great occasion for me to present what we have achieved so far and share with the community, of course. So let's talk about the overarching objective of such a project. So the idea is pretty simple to say, right? So it's enable a safe, efficient, and acceptable interactions between vulnerable road users and vehicles. Vehicles that can be considered from fully manual to some level of automation, but always considering there is a driver inside that might be more or less responsible for the interaction with these vulnerable road users. So why do we take a holistic approach? Because the underlying idea is that we get information and sensor data from many agents on the street, from many entities. So we get the pedestrians, we get the vehicles, the infrastructure, and the driver that we observe, of course. So we take the data from that and we inform and shape and create what we call the cooperative decision logic. The idea is that the interaction between vehicles and pedestrians cannot be safe unless we involve both parties in a sort of fluid interaction over time. So we need a system to understand all states of all involved agents. Is the driver distracted? Is the pedestrian with reduced mobility in a group, crossing where no crosswalks are present, etc., etc. So there are many conditions. So we need to be able to predict the intention of each of these agents involved in the interaction. The system, the cooperative decision logic, will also produce a resolution of the situation that takes into account the cost of the efficiency and the cost of safety. And will propose actions, joint actions to the different agents, mostly directly to the driver, who is, of course, carrying most of the responsibilities for a safe interaction, but also taking into account the information that is directed to the pedestrian. And we also keep track of the evolution of that interaction over time to ensure that there is no gap or discontinuity. That's why, in the end, we end up with two interfaces. One directed to the internal side of the vehicle, to the driver in the car, internal human-machine interface, that provides information about the recommended action, and one to the external of the vehicles, to the pedestrians on the road, that provide information about the intention of the vehicles, and allow, finally, a fluid interaction among the two agents. Now, more in details, the objective of the project is, first of all, to demonstrate this concept of fluid cooperative interfaces for driver and pedestrian. Second, of course, is to create these technical innovations that are necessary to make both parties mutually aware. Third, validate methods and create new methods that are necessary to assess the safety, the usability, and the effectiveness of the developed solutions. And last but not least, provide recommendations to regulation and standardization bodies, especially for what concerns the development of external HMI, which is not very regulated at the moment. Now, as I said, we are still halfway with the project, but I'm happy to be able to share with you some first results today. So one of the most important results that we have achieved, at least on paper, is that we were able to define, to structure the description of situations that more or less encompass all the possibilities, realistic possibilities of real life, taking into account the different types of driver, younger, older, distracted, attentive, etc. Taking into account different types of pedestrians, children, older, group of pedestrians, distracted pedestrian, reduced mobility, crossing over crosswalk signs or not, and most of all, adhering or not to the recommended action. So we also give the freedom, give the possibility to the agents to not respect what is recommended. So the system is resistant and resilient enough to be able to adapt and propose a new resolution of the situation. We also have produced concepts of HMIs, and we are now into the phase where we go less from the simulation side and more into the concrete implementation of prototypes. So what you see on the left is the concept for the internal one, what you see on the right is the first prototypes of the external one. Both sides have been designed to respect fluid principle of human-machine interaction. That means that they are all adaptive, inclusive, continuous over time, resilient, and unobtrusive. So they only provide information that is needed when it's needed and only if it's needed. With some differentiations, for the internal side, the system is also ubiquitous. It's a bit all over the places and multimodal. Whereas for the external side, there is a much more strict consideration for what is the current legislation and what might be the future legislations, especially in terms of visibility and reduced visibility conditions. Now, here you see short videos that show you the very first stages of virtual prototyping from both sides. So you see the multimodal system on the left for the driver that has head-up displays, LEDs, lighter, dashboard, etc. And on the right side, one of the many versions that are under testing of a combination of positions, display size, font size, visibility, etc., etc. Now, for the cooperative decision logic, so far we were working independently, internal and external side, because we had to understand what are the critical points, what are the critical nodes of the action, and how can each action develop over time, and all the deviations of that. Now, we are at the next stage where we are integrating that into the coordinated system. So without going into technicalities, we have to take two things into account mostly. On one side, we need to be able to represent in the cooperative logic as many scenarios and variations as possible. On the other side, of course, we need to make it computationally feasible. So we are working on both sides, and we have some interesting results already. Now, also a few words about the development of software, co-simulation environment, methods, digital twins. We have produced created a driver monitoring system that can not only detect the driver state, but also predict the intention of the driver. And also on the external side can recognize pedestrian and predict the pedestrian intention with explainable predictor in AI terms. What you see on the left side is in this small corner the predicted intention of the drivers to yield when a pedestrian is about to cross. And on the right side, you see both versions, the pedestrian view and the driver view of that avatar is actually a real digital twin of one of the project members. And what you can see is basically synchronizing time. When the pedestrian has the approaching car, he sees that the car sends a certain message. The message is interpreted, the pedestrian crosses the street, and the car moves on. Now, we have two more things in terms of software. We are developing the osmotic software layer, so-called, that works as wireless data exchange hub to basically take into account and coordinate all the information completely wireless from inside and outside the vehicle. And we also have validated some evaluation methods that works objectively and subjectively in both scenarios, so for real prototyping and for simulation environments. First results from some very small size sample study, exploratory study, show that we are basically going in the right direction, as we have subjective ratings that are pretty good of what we tested in different versions of interfaces that we tested in terms of usability, acceptance, and perceived safety. And also we have objective measurements that tell us that the reaction time when we use our HMI for older or regular driver are basically halved. From the external HMI side, we're also well down the path of development, as we have now created a co-simulation setup, which I've shown you in the videos. We are defining all car parameters and refining the messages, especially considering the physical limitations of such a prototype in terms of, as I said, luminance, resolution, font size, etc., which is definitely non-trivial. Coming to the impact session, dissemination, publication, as of course we are still halfway to the project, we don't have so much in that sense, but we have established a few important milestones. So first of all, we have established a yearly event that is taking place at our premises in Graz, in Austria, the so-called Fluid Human System Interaction Symposium. This year we're going to host in June the second edition, so of course you're all more than welcome to participate. We have established an advisory board, putting together members from industry and standardization bodies, including ethics advisors. We are now members of the Euro NCAP working group on human factors and HMI, and the IEEE Intelligent Transportation System Society. We are bridging technology and innovations, the concept that come from the fluid interface from the European HADRIAN project, that my colleague Peter Myrtle will present later today. And we have started, of course, to get out with publications in journal, conferences, etc. A couple of quick remarks. We have an honorable mention of one of our members, University of Alcalá, which was ranked 4th in an international student competition for this pedestrian behavior prediction AI system. And we've also given lectures on the fluid cooperative HMI at the Human-Computer Interaction Conference. Coming to the exploitation, with this is my last slide, we have identified 4 key exploitable results that encompass software concepts, systems, so anything that goes from TRL 4 to 6. And our plan is to, of course, engage stakeholders with all these exploitable results, which is what we are doing now. As said, as indicated by the red line, we are halfway to the project. We have engaged a few of the stakeholders, and we are ramping up in the next 6 to 12 months, engaging all of them with the respective key exploitable results. That's all from my side. Thank you very much.
Thank you very much, Paolo. This presentation indeed reminded us that despite the advances of the technology, prediction remains a very difficult exercise, because of the many actors involved and the different variations possible. I will now give the floor to our next speaker, Nicole Van Ness, who is joining us from the Netherlands. She is head of human factors research in vehicle automation department at the SWOG Institute. Nicole also holds a professorship in human-centered design for smart mobility at Delft and is member of the board of the TU Delft Transport and Mobility Institute. Nicole, the floor is yours.
Thanks, Anka, for your introduction. Welcome, everybody, to this morning session after a nice cocktail last night. Glad to see you all here. I will introduce you to the MEDIATOR project. I've been coordinating this project together with my colleague, Michiel Christophe. Here you see the picture, and he's also over there, so if you're interested to talk to him later today, you know he's around. So I thought, as this is quite a broad context, I spent one slide on a little bit of context for those who are not that much into the automation. So what we see is that we are in a transition to higher levels of automation. And this technology is very promising. It has a great potential. It could offer us comfort, it could increase the safety on our roads, and also potentially it could increase sustainability and inclusivity of our transport system. At the same time, if we look at the introduction so far, now it's being implemented on the road step by step, we see it's also introducing new risks. So most of us know this example of the Tesla crash in Florida, where the driver trusted the automation to drive autonomously, but the automation, the sensors failed to see the white truck against the bright blue sky. And there's plenty of examples across the globe of these kind of incidents. So that was the focus of the call that MEDIATOR answered. And so this is kind of the wider level approach. Let me see if this one works as well. Can this one be switched on? It's working? Okay, then I can be a bit more free in my movement. Anyway, so we are focusing on let's say, the human factors concerns that we see with this automation technology. It's that drivers get distracted, they can get bored or confusion about the mode that they are driving in. And that introduces new risk, and it could lead potentially to an increase in crashes. And we see that on the roads, but we see a similar introduction of increasing automation in other transport modes, and also operators of trains, planes, and vessels are coping with the same, let's say, human factors issues. So with the MEDIATOR project, we focus mainly on the road, but at the same time, we work on the issues in the other transport modes. So our core idea is introducing a system that we called mediator that's mediating between the human and the technology. And the basic idea is that the technology is still in development and it has its strengths, but it also has its limitations. And we as humans, we also have our competences, but we also have our weaknesses. So in this transition phase, the challenge is using best of both to take us in the best way through this transition. So that's what the mediator system is doing. And as a result, we developed, let's say, a prototype of the mediator system, as well as generic knowledge that's applicable for the different transport modes, and that aims at reducing potential crashes. So we've been working on this for 4 years. We rounded off the project in April this year. We were with 13 partners, half of them from industry and half of them from research. Quite good representation across Europe. The budget was 6.5 million co-financing or contribution from the European Commission. At the end of the project, we put together a short video to recap our results. So I thought that's a very concise way. So let's start with that one.
As you're surely aware, automated transport systems are developing rapidly. No wonder, automation has the potential to improve the safety, sustainability, and inclusivity of traffic. However, higher levels of automation also introduce new risks, such as mode confusion and degraded performance. This is why a European consortium of highly qualified research and industry transport experts developed Mediator, an innovative mediating system that safely switches between driver and automated system based on who is fittest to drive. Within a 4-year project funded by the European Commission, Mediator has developed working prototypes and validated the system in a number of studies, including virtual reality, driving simulator, on-road studies, and computer simulation. The mediator system continuously monitors the driver and the automated systems and mediates between them while taking driving context into account. Mediator has adopted a user-centered approach, which is accumulated in an intuitive human-machine interface design tailored to the needs and capabilities of users. Among others, we did so by supporting the driver's awareness of the automation mode by several cooperating elements, such as ambient lighting and LED strips. And the evaluation results are promising. Moreover, these results from the extensive testing of the mediator system are publicly available. With feedback from industry and policymakers, Mediator has developed guidelines for measuring degraded driver performance, guidelines for safe user-centered human-machine interface design, and roadmaps for further exploitation of the system. This is how Mediator helps to pave the way for safe and reliable future vehicle automation. More information, please visit mediatorproject.eu.
So that's in a nutshell, an overview of the project. For this presentation, we kind of reviewed all the results, and there's a lot after 4 years of hard work of so many partners. And we thought for this presentation, it's probably best to use the opportunity to share some of the main concepts we've been using that we feel, based on our experience, are worth taking further beyond the project, so maybe people can benefit from it. So this is one of the concepts that we developed in the proposal phase, and it's what we call the driver automation fitness plane. What it shows on the X-axis, it's what we call the fitness of the driver. And by fitness, we mean its ability to drive. So fitness could be decreased when someone is fatigued, but also when someone is distracted. We call it that this driver is less fit. So on this X, you can see the fitness of the driver, and to monitor, to bring us through the decision, it's important to continuously monitor this fitness of the driver, to see if the driver is fit to drive and which capabilities of the driver we could use at a certain moment. On the other X, it's the fitness of the automation. So also the automation is potentially available, but it's not fit to drive in any moment during the trip. So, for example, depending on the ODD and the conditions, it could be fit or less fit, and also the weather could influence the fitness of the automation. So in this plane, what you basically see is that you can define different quadrants, and it helps us how to mediate between the human and the driver. So if you look at the green corner, so to say, this is when the automation is fit and also the driver is fit. So this is a very luxury situation. So both the human and the automation could potentially drive, and there's something to choose. So the driver could choose, and this is also an opportunity where really comfort could be offered to the user, because the automation could offer to drive and take over in any condition. Also shared control could be introduced here, which is, I think, a very strong and meaningful concept that's a bit underrated at the moment, but there's a huge potential, I think, to explore that further. Then if you look at the upper right corner, the red corner, that's when both the automation and the driver are unfit to drive. So this is a situation we clearly want to avoid at all times. So that's also, if we monitor both of them, we can see when you're heading that direction, when we're heading towards the red zone, and if you're moving that way, that also learns the mediator any action needs to be taken to prevent arriving in the red zone. So either the automation should be, let's say, upgraded or switched on, or the driver should be alerted. So if you're moving to the right in this diagram, then the driver reduces in fitness, but the automation is fit. So in that situation, the automation could take over. So that could be a driver-initiated or a vehicle-initiated takeover to make up for the driver's condition. And in the other way, if the automation gets unfit, then we have to make sure that the driver remains fit. So the basic idea is that you continuously have to measure the fitness of both the driver and the automation. And then part of the research was to find, let's say, the critical markers, which are the minus and the question mark, to find the markers when we think the driver is fit enough, when the driver gets degraded, and when it's really beyond the minimum acceptable level of performance and an action is really needed to be taken. So this was part of our project to find out how to measure driver fitness and also what are the critical markers for driver fitness, and the same for the automation fitness. Also based on this diagram, the mediator could decide when to switch between the human and the automation, and when a handover would be desired. That's something we could learn from this diagram. And then to manage these kind of transitions or other actions, like there were preventive actions to wake up the driver when you see he's getting degraded, that was all done through an HMI. So there was also a severe emphasis on defining the HMI design. And within that approach, we looked at corrective action. So when you see a driver is degraded, what can you do to kind of wake up this driver? But we also try to find some preventive actions, to be proactive. If we know this is a condition where a driver is usually prone to fatigue, let's try to see if we can engage the driver already to prevent the fatigue to happen in the first place. So this is one of the main concepts underlying our mediator project. And we translated it to this schedule of the system. It's our conceptual approach. So what you see here is that the upper loop shows how we measure the driver state, and the lower loop is the measurement of the vehicle capabilities. And then we also measure the context, because depending on the context, other requirements are needed from the driver. And then in the center, it's the mediate control. It's where the decision logic takes all the signals and decides what needs to be done. And then the output is the signal to the driver, which is given through the HMI. So this is, in the project, this was, let's say, a separate system, but in general, it's more a conceptual idea that could be integrated in the automation. So within the project, we did work on the holistic HMI design to create a user-centered HMI. We worked on automation monitoring, on driver monitoring, on the decision logic development, and also on the impact and exploitation. So for today, we decided to focus on one of them, and we chose to focus on the holistic user-centered HMI design. So I will share some of the results from that area. To start with, when we started thinking about this human-centered HMI design, we found it really important to take a holistic approach. So we think in this transition, what's really needed is to go beyond adding an extra icon on the dashboard. We should really take a holistic approach and look at the integral experience of the driver and use all the senses and opportunities. Well, not necessarily use them, but explore the use of them and see what would be the best combination to communicate what we want to communicate. So there were two key concerns that we found most important to communicate to the driver, what we think is most challenging in this transition. Because what we will see is that there will be different modes available in the vehicle during one trip. So therefore, it's very important that at any time the driver is fully aware of the mode he's driving in. And also the transition between that mode needs to go really smoothly. So then we arrived at the stage, okay, which modes do we communicate? And we all know these levels of automation. So that's most logic to take this as a starting point. But when using this approach, we found it really doesn't work to take this as a starting point for a human-centered design, because this is a very technology-driven perspective. And from a human-centered perspective, actually, this happens not to make that much sense. So it's really technology-driven in a way that it clearly defines the steps of technological development and how new technology is introduced step by step, and how step by step also the role of the driver decreases. But it's really taking the perspective of the driver, does, let's say, the rest and the remaining task. But this remaining task is not necessarily what we are as drivers are good at, or not that we find it convenient. So within the project, we thought we have to take the driver as a starting point. From a driver perspective, start with the driver skills and limitations, and taking that as a starting point and see how technology can support. So we thought it's good to focus on the development of an intuitive user-centered interaction and take really the human perspective. So the human has been the starting point, and from there we try to define what's really most important for the driver that is being communicated to this driver. So from there we developed the mediator driver mode, and there were two key elements in this driver mode. So we thought first and foremost, it's most important that it's being communicated which mode the driver is in at a certain moment in time, and what requirements are connected to that driver mode. And there we thought actually there's only one clear distinction, and it's either the driver is responsible in the end, or the automation is responsible in the end. And in the first condition, where the driver is responsible, there could be all kinds of levels of support by ADAS kind of systems, but it should be clear that in the end, the driver is responsible. A second important thing is when the automation is responsible, that the driver needs to know for how long this condition is available. And that's what we call the time budget. The time budget indicates for how long the automation is available. And based on these two conditions, we shaped 3 levels, or what we call driver modes. So the left one is what we called continuous mediation, and this is actually when the driver is responsible. So there is a continuous mediation by the different systems that could be switched on and off, but in the end, the support could be higher or lower, but it needs to be clear that the driver should be alert and able to being responsible. Then there's the second condition, which we call the driver on standby, and this is when the automation can drive autonomously, but only for very short times, maybe seconds, up to a minute, and also with a high level of uncertainty. So it is okay for the driver to take a short period, to take a glance of the road, sending a WhatsApp, but you have to be on standby. You know you can't pick up on a larger task because anytime you need to be able to take back control. And then the third condition is when you know you have a longer stretch, maybe 10 minutes, 1 hour, up to a couple of hours. So then you know, okay, now I can really relax, I can watch a movie. So you can chunk a bigger piece of work within that period, and you can rely on the automation that you don't have to take over within a short notice. And then you can see this, let's say, time budget somehow communicated, so it counts down, and then it slowly takes you back to, let's say, the driver in standby mode. It's a smooth transition back to the manual driving when needed. So we took these principles and based on that we designed an HMI design. So we explored the different modes of transport. This work was led by the TU Delft Industrial Design Department. And we really explored, let's say, also vibrations, the steering wheel retraction, the seat belt, we used it. And also we tried to use a lot of lighting. So we decided in the end to use this ambient lighting to communicate the different modes. So it's really in the peripheral continuously present, and it really sets the scene to whether you can be active or more passive. And yeah, there's lots of elements working together. It goes a bit beyond the scope of this presentation to further work on it, but I think it's really a step forward in finding new ways, more holistic ways to communicate with the driver. And yeah, it was an interesting result. It was also interesting that last week I got a picture of a friend of mine sent me a picture. She said this is the new Tesla 3 model. So it was interesting that there was very much a similarity actually between, well, their solution and our solution. To develop the user interface, we took a design approach. So this is also what I think was really original, and also something that I think the field could benefit from more. So we started with the human factors knowledge that we have in the field. And then we asked the designers, based on that knowledge, to come up with creative solutions. And together with, we did some, let's say, co-design between the designers and the human factors expertise. And in different iterations, we developed, in the VR setting, we developed prototypes. And when we felt that was a kind of mature and all the human factors knowledge was well integrated in this first prototype, we did further co-design sessions with the users. So we exposed the users to the interface design, and we asked them to think out loud how they interpret the different signals. And based on their thoughts, we could see to what extent our user interface was being understood, and we could adapt it. And in a couple of iterations, we could work towards a satisfactory understanding of this design. So this is one example, and well, I could talk for hours, but I only have 3 minutes left. So we implemented all the developments we did in 2 driving simulator studies, 2 on-road testing studies. We did VR study and we did computer simulations. And all of that results, we did, let's say, a comprehensive evaluation of the concept and the implementation. We learned that in terms of impact, we think this mediator concept is a significant step forward towards a safe transport system. It leads to a reduction in crashes, and we see a decrease in distracted driving, we see improved mode awareness, we see enhanced takeover rituals, we see support drivers in self-regulation, and also migrate the impact of fatigue. And overall, we got really positive feedback from the different participants, and we expect a high acceptance and usability scores. So in conclusion, there's 4 main concepts that we think are worth further consideration. It's the mediator fitness plane, it's the mediator system concept, it's the mediator driver modes, which I think is a first step towards development of human-centered driver modes, and it's the holistic design approach and the iterative approach there. So one final remark, also what we found during this project in the discussions between ourselves, there's really a need for changing perspective. So I think, like I said in the beginning, the automation has much to offer to our society. It has the potential to increase the safety. It has the potential to increase sustainability. And it has the potential to increase inclusivity. But it's not bringing there necessarily. So if we want to get there, we should focus on these societal goals. So we should go from a transition which is driven by technology, from a transition where the societal goals are driving the technology. So the societal goals should be our objective, and in the end, this technology is a means to an end to get there.
Thank you very much, Nicole. I think nothing can be added on this very comprehensive and clear presentation, and I also like very much your conclusion on which we see that the society should driven the technology, which is a tool for better innovation and progress. Without further ado, I will give the floor to our next speaker from the project FITDRIVE, Martin van Gasteren. He is Research and Innovation Manager in the ITCL Technology Center in Burgos, Spain. Martin has a long experience on behavior and safety on driving simulators as a tool for data collection, and he will introduce us to the work done so far in 2 years of FITDRIVE project.
Yes, thank you very much, Anka. Good morning, everybody. So FITDRIVE, monitoring devices for overall fitness of drivers. Quick slide on project information, 3.5 million euros of funding over 42 months. We have 1 year to go until February next year. And with a fantastic consortium, world expertise. I always say I'm only the coordinator, but they do the real work. 3 industry partners, 3 stakeholder associations, 2 universities, and the technology center, which is ITCL, and the coordinator. So, quick view into one pilot, so to set a bit in what we were working. You see a van driver with loads of sensors there measuring how he is driving, and also a simulator of a truck in this sense, in the same setting in a virtual mode. So we focus on professional drivers, mainly on van and truck drivers, as you just saw. We try to identify and eventually prevent impaired driver states. And we use AI technology to analyze all this. So there are driving tests in simulators, also on the road on test tracks. And there's quite some literature out there, of course, on impaired driving states. We'll use this and then make a profile of usual daily driving style of these drivers. And then, of course, with the AI techniques, we can detect when a driver gets out of this personal driving style, which is an indication for impaired driving, okay? So the system will do then continuous real-time screening of psychophysical capabilities and vehicle parameters, give an indication of the fitness to drive, to detect the onset of fatigue and other altered behaviors. But the onset, so even before the driver notices drowsiness or whatever, already we try to find some indicators to detect it very early and in a personal manner. And the system will then continuously keep on learning and adapting on changes on usual driving style to improve also the detection of impaired driving. So different aspects of the FITDRIVE system. So there's neurophysiological models of the onset of these alterations with data from brain activity, from heartbeat, eyes, skin data, the sweating, you know, vehicle data. OBD port, the CAN bus, and a smart tachograph, which is also being developed in the project, with indicators like acceleration, position of the steering wheel, the pedals, and also much more sophisticated parameters from the vehicle. There's a cloud-based AI system to detect these altered conditions. And then there's, through the smart tachograph, a connection to police roadside controls. So this can help the police to communicate with the vehicle and receive an indication of the current fitness to drive of the driver, so they can select which vehicles do we want to stop and have a check on. And another development is a mobile drug screening device for a very quick detection of drug use, also used by the police roadside controls. And we aim at contributing at the standardization of levels of different levels of fitness to drive, and pave the way for fitness driving assistance systems. So some preliminary results. As for a simulator and digital twin, which is, well, you can name it like this as well. We can discuss about that, but okay. So we did pilots in Italy and Spain, in Rome and in Burgos, and in Leon in Spain, with 18 participants in each site in the simulator, and then on a test track on a circuit with actual vehicles, vans and trucks. And this was a subset of the participants in the simulators. So the virtual circuit in the simulator was an exact copy of that circuit. We used 2 ITCL simulators there, coming from the SimiSafe project and the Mindtooth project. One was used for the van, and the other one was transformed into a truck simulator. So, and in these settings, we collect this data triangle, we call it. Actually, in MEDIATOR presentation, we also saw a very similar thing. So data from the user, from the vehicle, and from the environment. We try to keep the environment as constant as possible and really focus on users and vehicles. The environment has, of course, influence on the state of the driver. At night you get tired more easily, but that is a cause. And the symptoms of actual, impairment to drive, that is noticed in the behavior of driving, and so data from the user or from the vehicle. Okay. So this is where we look for this onset of fatigue. And next September in France at the DSC, the Driving Simulator Conference, we will present this simulator and this data collection system. Okay, so current status and some preliminary results. So in the tests for fatigue induction, we were able to do this. Actually, in the simulator in Italy, one participant fell asleep. We heard a bang on the head on the steering wheel, and actually fell asleep during the test. So this worked very good. We saw that the EEG signals, the brain activity, is very good, gold standard. And it delivers a ground truth for your AI on what is fatigue. And with input from literature as well, then we try to correlate different features with parameters that you can obtain with non-invasive sensors. You don't want a truck driver with an EEG on his head driving all day, of course. So if you can relate it with heartbeat, for instance, then you have a smartwatch or a steering wheel with a heartbeat sensor in it, and you can use that one. And then from parameters that we have, make a selection of which features can give us indications on the onset of fatigue or other impairments. So what is coming up still in the coming year is do personalization pilot. So I have drivers, new drivers, driving for 1 month in Italy, Spain, and also Ireland in this case, and do tests on the detection of unusual behavior. So this is work in progress for the coming year, as I said. And yeah, so far there's several publications already on this AI modeling we do, the neurophysiological measuring of mental fatigue. And something we stress a lot in, we work a lot on, is the need for standardization here. We need common criteria to measure reduction of fitness to drive. This is a message I want to convey today. This exists already for alcohol. You're allowed to drive with a certain, promillage of alcohol in your blood. This does not exist for fitness to drive. So we need to have a good measurement and define what levels are allowed and not. And yeah, put a mark here on the countries. For alcohol, there's different laws in every country. If a truck driver goes from one country to another, he faces different legislation, which is, we should try and avoid it and have a common, at least European, standard on this. So, most probably this will not be one measurement, like with alcohol in your blood. It will be several features, and then you can think of, if it turn out to be 5 features, you see this blue area, which is the allowed area. The yellow line would be a measurement of the current driver state. One value is outside the blue area, so this means some form of impairment. So, some examples of the use of this fitness to drive standardization, what levels are allowed. Of course, the driver must be warned if fitness to drive is reduced. Also, police roadside controls, I mentioned already. The police need to know at what levels should I, take action, stop the vehicle, or, fine him or whatever. And also in automated vehicles on level 3, we saw before, so that the vehicle can decide to give the control to the driver. The driver must then know what the fitness of the driver is before, perhaps he should stop the car instead. So action we've taken to promote this standardization needs. We organized 2 meetings at the European Parliament. They are working on the new driver license directive right now, and this includes fitness to drive. So, yeah, we had discussions there. We conveyed the message, and well, we're a bit proud to have been there. Actually, it's very good. Yeah. Also the EUCAT exhibition in May last year, which was focused on the automated driving, of course. TRA in 22 in Lisbon with our sister project, Panacea. This is where we shaped this idea of standardization and driver interaction. We organized a side event at TRA 24 in April, a stakeholder event there, okay? So expected mid to long-term impact. So eventually, for professional drivers, have AI models and a solution for detecting of individualized and the onset of reduced fitness. And also, there's this new drug screening device, which has very quick measurements in less than a minute. Actually, currently it's like between 5 and 8 minutes to have a drug test, so this is a good time win for the police. Then, as a consortium, we decided on an open research approach. We want to achieve a wider impact on this. So our results will be available publicly, because then we'll have a better outreach to administrations, to regulating bodies, to work together. Also, industrial uptake will be much more likelier. We can try and connect with, I don't know, BMW and try to sell our system and so on, but between the end of the project and actually implementing it in a car, there's years and years of work and so on. And in practice, this is very unlikely to succeed. So we think if we openly publish our results, our findings on how this system works, what is good, what is, what is still to be worked on, all OEMs and other car industry companies, they can, you know, pick it up, integrate it in their own research, which they are doing. They are also working on this. We know that many cars have, you know, every brand has its own fatigue detection system, but, you know, perhaps they can use our research to improve it. Then what's in it for us? We give everything away. You know, the drivers will individually exploit their systems, which is of each partner, their core business. So the drug screening device, the smart tachograph, there's a communication device we call Bridgebox, and the simulators. And we think like this, we'll have the maximum impact. So last slide, discussion, a few points that, well, since we're going to the discussion now, a few topics that I'm interested in. I hope we can discuss about it a little. So the standardization of levels of fitness to drive, if anybody has any input, ideas, experience with it, I would be very happy to hear this. Here's a question, so for professional drivers, fatigue seems by far to be the main cause of reduced fitness. So I'm talking about professional drivers, right? Truck drivers and van drivers and so on. So drug use and use of medication that causes impaired driving seems to be far less relevant. So, but we know this from practice, from the field, but we didn't find any research that confirms this. If anybody has any knowledge of this, I would be very happy to hear this. And the last point, I think last, on the police roadside controls. So we try to help these improve, but it's very hard to find information on effectiveness of these police roadside controls. So the average duration, how much people do they catch, where they detect actually influence of medication or whatever. And also the impact for the transport industry. How relevant is this? Are these delays the cost of stationary times of their trucks or their fleet? Does it have any real impact, or is it not that relevant? So with this, I thank you very much. Here's our information, and happy to discuss. Thank you.
Thank you very much, Martin, and thank you to all speakers for having kept their time. It means that now we have a sensitive amount of time also to discuss with you, and for this I will give the floor to Magnus.
Thank you very much. And now we've seen different aspects related to the human factors. We've touched on this from various angles, and I hope then that you are all fit to ask some questions, because that's really what we are here for now. So who would like to start? Let me see some hands, please. Yes, we have several hands. Chark, do we have a microphone? Yes.
Yeah, thank you very much. I'm Jack Hotzinger, Toyota Motor Europe. Thank you for the presentations in the early morning. I have a question for Paolo on the HEIDI project. External communication to vulnerable road users, mainly pedestrians, I guess you were showing here. My question is, do you plan user studies on that? How it is perceived, how the effectiveness is? Do you think about KPIs? Do you have really practical design guidelines or something? Sorry, 3 questions in one. Sorry. Maybe your picture.
Okay, can you hear me? Yes. Okay. Thank you very much for the question. Yes, indeed, it's a very challenging part. As I said, some of the objectives of this project is not only to propose a concept, right, but also to demonstrate the technological feasibility of that. So that's why we're having prototypes, and we are creating this co-simulation system. So it's a hybrid setting where you will have real pedestrians and simulated vehicles, or real vehicles and simulated pedestrians, or both interacting by interaction is mediated by a virtual reality headset. So there are already similar facilities out there, And so we know that it is somehow feasible. Of course, here the additional challenge is to coordinate time-wise the information to the inside and to the outside, right? So because the interactions between pedestrians and vehicles is over in a few seconds, essentially. So it's very important, as Anka was saying before, at the beginning, the ability to predict what is going to happen or to come up with possible scenarios, propose immediately a certain course of action. But what happens if the driver is not responding correctly to the, is not adhering to the recommended action, then the system needs to escalate or need to propose a different action. And then what happens at the same time to the outside, right? So, so we have a very asymmetrical communication system, because there is one part that is very dangerous, the vehicle, and one part that can only be damage the pedestrian. So this, as I said, via this hybrid co-simulation system, we plan to cope with these challenges. Right now, we're basically done with the first preliminary investigation phase that was done exclusively in simulation. And as you saw in some pictures, we're already building the physical prototypes. So we will have the BMW that will build the internal HMI system in one of their vehicles. And we will have Marelli that will build the external HMI system in one of their vehicles. And then we will have Honda that will also be able, with the RoleIntegration University, to create this co-simulation setup where we can basically put both of these systems inside. And then we can have pedestrians that are walking physically inside a space that is large enough to allow a car and a pedestrian to cross. And we have real-time motion capturing system for whatever is happening inside that room. So this system is right now almost finished. And so we plan that by August to have the first concrete results on a real setting. By the end of the project, we'll also plan to have demonstrations with everything running for real. Does that answer the question?
I'm not exactly sure.
Okay, yeah, me too. But I'm not exactly sure it is possible.
I think the internal communication you explained very well in your presentation, but the external communication, I'm not exactly sure yet. So you will develop design guidelines, you will have prototypes, and you will evaluate with KPIs the effectiveness of that external communication.
Yes, starting from very basic aspects, as I said before, right? So the actual design, so how many pixels does it need to be in order to allow certain visibility from a certain distance in the real world, and what about if it is dark, if it is foggy, etc., etc. From color aspects, from size of display, so all of that is right now under investigation. As we have already, actually what you saw in the pictures are two different prototypes. One is, let's say, a high resolution, and the other one is a high visibility, let's say, and that are not the same thing. The idea is to implement both of them at both sides of the vehicle for the front of the vehicle. And all these are choices that we need to make to, on one side, account for what is the real feasibility of the system, and on the other side, to cover all the possible dangerous scenarios. It is very unlikely that you have a dangerous situation with a pedestrian crossing on the back of the car, so we do not investigate that, right? So the danger is on the front, etc. But also other aspects is how do you get the right pedestrian targeted? So how do you know that I'm addressing you and not the person beside you? So that is also one of the systems that we are developing, which I did not present here because it is right now still in a sensitive phase, let's say. But the idea is to be able to come out later with also indications for regulations in that direction. So how can you specifically target pedestrians that is on the right and not the pedestrian that is on the left of the road, for example?
Good, thank you. And you can continue at the coffee break, so no problem. I think we have one there, and then first we had someone far down. Yes.
Thank you. Carmelo D'Agostino from Lund University, Sweden. And I have a question for Martin, FITDRIVE. We have a similar project, I mean, one of the work packages like this for as a research innovation action for collaboration with Africa. And I thought that in Europe we can have an easier control on fatigue for professional driver because of the vehicles. And the vehicles can help in registering fatigue or at least give input on what's the level and take some action. Do you have any input on this? Or did you consider?
I could not quite understand you. I'm sorry. If you can please repeat.
Yeah. When you evaluate fatigue of the drivers or the effect of fatigue of the driver on the performance, driving performance, vehicles can help in registering fatigues or try to understand what is the fatigue level of the drivers. Do you consider this, that vehicles or technology can in some way help in the identification of fatigue level?
Yeah, so if I understand well, the fatigue level measurement, this is indeed what we are looking for. So we try to find different parameters from the user and vehicle that can have indication of this fatigue level. Yeah,
but when you don't have the help from the vehicles, there is any other way to measure fatigue?
Yeah, from the driver data. Yeah, from the driver there are a lot less parameters than from the vehicle. So just by measuring data coming from the driver will be difficult to detect fatigue levels. We can have indications, yeah, but to have a more robust detection, vehicle data would be needed.
We are trying, just to let you know, I don't know if we are in the right direction. We are trying to evaluate the driver performance by naturalistic driving observations from outside the vehicle. But that's a bit more complicated.
Yeah, according how we are doing it, it will be very difficult because, as I said, for a lot of vehicle data that we record is really from the, from the system of the vehicle itself, which is, things like lateral acceleration, longitudinal acceleration, the speed of the engine, and those kind of things, braking activity. This is hard to detect from outside. This would require a different approach.
Yes, please.
Thank you. Hi, Natasha Merritt, University of Leeds. Question, comment to Martin. I do completely agree with you about fatigue being a massive issue regarding fitness to drive. One of the problems, especially with the kind of drivers that you're describing, is that they're under pressure to perform. So I'm just wondering how much you're engaging with organizations and if there's anything you're doing that helps them before they get in the car. I think we've all been in a situation where we just go, I'm really tired, but I'm just going to get home. So is there sort of something around that they have an understanding of the consequences before they actually get that far?
Yeah, definitely. So, so there are 3 associations in the consortium. European Professional Driving Association from Dublin. There's the European Driving Schools Association from Brussels, and AIPSS, which is an Italian road safety organization. So yes, we are very much aware and in touch with professional drivers themselves, and indeed it's a major issue on the lifestyle that people have. So long shifts, irregular shifts, irregular food, low quality food, the physical work of unloading a truck, for instance. And as for the van drivers, the pressure is very high. For truck drivers, it is, but van drivers, you know, with constant control of their delivery company, about any step that they take is registered, and every second of delay is, you know, is notified. So yes, indeed, this is a very important factor for fatigue. Yes.
Yes? Where's the next hand? It's down there.
Hello, good morning. Sven Janssen from TNO, the Netherlands. I see a lot of use of simulation and virtual reality, and I'm wondering, and also there are very much specific scenarios. So I'm wondering, what can we do with real life in traffic assessment? So what do you see the challenges of doing assessment of these technologies or these development in real life traffic situations, and how could the results of that complement the results that you are achieving from the simulations? Just, it accounts for all the projects, I think.
So within the Mediator project, we were keen to have the system tested on the road. Though, as you still need, let's say, driving automated mode, it was challenging. So the way we dealt with that is that we developed 2 on-road prototypes, and one was more testing, let's say, the technical system. So it was the measurement of the driver fitness and the measurement of the automation fitness, and the switching between those systems based on, let's say, a prototype of the mediator decision control logic. And that vehicle was driven in real traffic, but by professional drivers. So they knew how to deal with it. For the user interface, we found it really important to have naive users. So there we instrumented a Wizard of Oz vehicle where we implemented the HMI. And with that vehicle, we took participants out on the road to see how they responded to the different scenarios that we implemented in the real road. So that actually we used to complement our simulator and VR studies and to evaluate the prototype in the real traffic. Does that answer your question? Or?
Can I also comment on this?
Yes, please.
So we also used both simulator and on real track on a test circuit, actually, so not a public road. The thing with the simulators is it's very easy and quickly to set up it's tests and with more participants for that case. And also the data that you obtain is a lot cleaner, so it's easier to work with. Yet it is a simulation, it's not real life, so in the tests on the real track you have data that's closer to reality. And so that's why we use both. And also from previous project, the SimuSafe project, we know a lot about the bias that a simulator introduces to the driving. So we use this to do some corrections on the data as well.
Good. Paolo, do you want to comment from your perspective as well? If you have any additional...
Yes, from my point of view, I would like to stay a bit more general because I think that the question is about how do you get from simulation to real world, right? And I think that's a question that is very general and that is valid in many contexts. So the idea, I think, is that we are taking a building block approach, right? So step by step. So can we promise, can we commit today that we will be able to do it exactly as we predict next year? In reality, no. To be honest, no, right? And I think that no one can commit to that. But we are trying to improve the simulation to get more and more close to reality. We are trying to introduce complexity in the simulation to get more and more close to the actual complexity. But on the other side, we also need to build the awareness, to build the acceptance of those technologies. As Anka asked at the beginning, right? So how many are using systems that are on the market for now 20 years? pretty much, and we only have a few respondents. And how many of them use it daily? Even less. So this is the rate of the process that we're dealing with. So we need to work constantly towards that, but it's a long-term goal.
Good. Thank you. Oh, yes, another one. I don't need to use my own questions. That's good. Please.
Yeah, thank you. Tom Alken from MapTM in the Netherlands. I guess a question for you, Nicole. In determining the fitness of the driver, is the method also context dependent? So I can imagine that for different situations when you have to ask the driver back into the loop, maybe you would need different levels of fitness. If you're in a complex situation, you would need a higher level of fitness.
Yeah, that's exactly the case, actually. So this fitness plane, as I explained it in the presentation, the level of fitness needed really depends on the context. So that's for both the fitness of the driver and the fitness automation, very much depend on the context. So we worked that plane towards a three-dimensional cube, actually, but that didn't fit in the 15 minutes for today. But yeah, context is really important, and also it's another challenge how to measure the text, and how also in that measure to define markers that are relevant for the performance and the fitness of the driver. But in the mediator system, in the figure, you also see 3 arrows of input, which is the driver, the automation, and the context. So that's another, let's say, field to master, how to define it and how to measure it.
Because maybe a follow-up question was, how do you determine, for instance, you mentioned 3 different states. So one state, the driver could sleep. Can you say something on how would you determine for a, let's say, a longer period of time that the vehicle is actually not going to encounter a situation where a takeover is needed?
Yeah, so how we see this concept of the mediator, so for now I focused on that we want to measure the fitness, but actually beyond that we think it's important also to predict the fitness. So you want to go beyond measuring the fitness at this moment in time, but also being able to predict this fitness in the near future and if possible in the longer future. And from that there will be a prediction with a certain certainty or uncertainty. And based on that, you know, at some stage, these windows of automation, these windows where automation can be offered securely, can be derived, so to say. So it will always be, let's say, a combination of probability, but I think there you have to be on the safe side, that you only offer it when there's high probability that it can be offered. And that could be, in the end, also a combination with connectivity, to make sure the system is really robust and reliable. And otherwise you communicate, let's say, the lowest time budget, and the time budget doesn't necessarily have to be, let's say, fixed. Maybe it could be when you, at a certain moment of time, it could be half an hour, and maybe after 15 minutes, it's again half an hour. But then you know, I have at least this half an hour. But that's what the system can give you for sure, so to say. And if it's only 1 minute, it's 1 minute. But maybe it stays 1 minute for 15 minutes. But that you don't know. There's the uncertainty. And then you know you have to be on standby for that period of time. Yeah, we've been thinking whether you could also communicate the uncertainty, but we thought probably then you will overcomplicate things again.
Yes, further questions?
Hi, I'm Gal from Correction. This is for Martin. I want to know how did you label the fatigue level with the driver? Did you use the KSS, and how did you do it during the drive? And the second question is, if you talk to players in the fleet market, what was the level of fatigue that they are interested in? Is it 8 or less than that, because they are professional drivers and so on?
So on the first question, for fatigue, we used unsupervised learning. So we have a lot of parameters that potentially could have some influence. Put them in the AI, and there try to find correlations. And so we get clustered data of different driving styles, as to say. And then what we use is if the 75% of the time, for instance, drivers in one cluster, we can assume this is the usual driving. And then in other clusters, this is altered driving. And then we can use measurements we did, the neurophysiological data, to try and correlate, okay, these samples are in this period of time, where with the EEG, we noted that there was fatigue detected. So we can make these correlations. This is how we create the models.
When you will take this product to the market, you will not use the EEG helmet or a sensor, right? So how can you then understand if the driver is fatigued or not, is tired or not?
Yeah, so this correlation to the non-invasive sensors, we are currently working on this. We have some indicators, like the heartbeat is a bit lower when you are fatigued, we noticed, and the smoother driving is less fatigue, so if there's more interruptions, those are in the indicators that we have, but this is work in progress now.
Okay, we are reaching the end of the... Was there another hand? No. We're reaching the end of the sessions, and thank you very much for all your questions, and thank you to the speakers for providing me with your impacts, because that's something I need to put into the notes. I do have maybe a couple of questions. We have a few more minutes. So Nicole, anything that you would like to pass on to the two others, because they are still running their projects?
In terms of project management, you mean?
Well, that could be, or it could be also any other types of learnings from your project that you see fit into the two other projects.
Well, I think there is a clear connection to sister projects or brother projects. Let me see if there's a main takeaway. I think we're both focusing on fitness. So maybe there it's worth actually to think a bit more. Sorry, you press it?
Oh, sorry.
You're fighting on.
So we can think about maybe, I don't know if you've seen our deliverables, but otherwise it could be interesting to have a look, and maybe better even to have a talk with those researchers within our consortium working on that topic. And for you, I was also actually thinking of a question, as you are also very much in the HMI design. I really like the approach, and I think it's a really important topic that you're focusing on. And this external HMI is really the next challenge that we are facing, also building understanding and guidelines like we're asked in the audience. So what wasn't clear, but it's a question like, you say you're looking at, let's say, technical conditions for the HMI design, like the luminance and the pixels and stuff. But you also mentioned that there's, let's say, different situations where you need to communicate. So I was wondering, did you think about developing a kind of taxonomy? What kind of situations, what kind of message would be required? So there could be like a taxonomy of different messages to be conveyed, and then also explore kind of solutions, how this message could be conveyed in the most effective manner, going maybe a bit also beyond the display on the front desk, but also using other implicit and explicit messages to explore how to communicate that in the best way. And then I think that could give insights, also working towards those design guidelines that I think are really needed by both industry and policy, actually. So
that sounds like a complete project.
Oh, maybe an idea for the next call.
Indeed.
Do I need to press this one? Yeah. Okay. Yes, indeed. Those are all very, very valid points. And yes, we are developing this taxonomy because it is, I went very quickly through the slide, but it is indicated as one of the key exploitable results. So providing this, creating this catalog, we call them catalog, but it's essentially the same, of the same nature, right? To provide this understanding, which is not only about the technicalities, right, that allow the correct perception, let's say, but also in terms of really messages. So how do you get that message across in a safe way, in the correct timing? What is the correct timing for communicating to external road users, especially considering that you don't always have the perfect ready-to-react pedestrian, but you have a variety of situations, coming back to the complexity of real life. So we started with the taxonomy of the scenarios, right? And we're now developing the taxonomy of the messages, which is a core part of this cooperative decision logic. It's funny to know that also from your slides, we're using very similar labels also for the systems, right, and the solutions. So I think that there can be really a lot of synergies and a lot of developments in that direction. Yes.
Yeah, and I think also like it's the initial message, but like you said, if it's maybe not the desired response, then is an escalation needed.
Yes.
So also shaping this, let's say, iterations between the external road user and the vehicle to get, you know, where you
this is exactly the main function of the cooperative module, which basically needs to check which level of escalation you're reaching to the inside and to the outside. And of course, the logics are completely different because also the action possibilities are completely different, whether you have a driver or a pedestrian. The pedestrian cannot really do much to avoid to damage the car, but that's everything on the other way around, right? So the driver can do a lot to avoid hitting a pedestrian. So, and so these asymmetries, the timings are different, the reaction times are different, the action possibilities are different, and so this coordination is so the cooperative part is exactly about this coordination.
Okay. Thank you very much, and thank you to the speakers, of course. And thank you to you for asking the questions. And now we have half an hour break, so please be back here and grab some more people to join for the second half of the human factors session. So welcome back.
Good morning to you all. I think we shall start. It's already 25 to 11 to 12. So my name is Patrick Mercier-Handisyde. I work in the European Commission in DG Research Innovation, where I coordinate road safety research activities. And this is a follow-up session on the previous session we had on human factors in transport safety. So we'll continue this stream of research and innovation. I think human factors and errors linked to human factors are still clearly an important factors of accident on our European roads. And I wanted to come back to what Ancuta mentioned in her intervention linked to the use of advanced driver assistance systems. There was a report last year from DICRA, this a technical inspection company in Germany, who mentioned in their report at the end of last year that a lot of accidents are saved by ADAS system, but also a lot of accidents are due to the bad use or non-use of ADAS systems. So this is something we have to take in mind and shows that we still need research innovation in this field of human factors. So today, now we will have two projects which will be presented in a sequence. Will be half an hour of presentation, and then we'll have Q&A sessions. Just as a practical thing, we will need to have your mics when you speak and when you ask questions at the end, because it is registered, and there are also outside persons who may intervene in that session. Without further ado, I would like to give the floor to Peter Mörtel, who is the coordinator of the HADRIAN project, which is a H2020 project. Peter is a principal researcher on human system integration at the Virtual Vehicle Research Center in Austria. So, Peter, the floor is yours.
Thank you very much, and thank you very much for attending this last session prior to lunch and almost the last one in this conference. So I will try to be on time. So yeah, I will present our project, and I would like to start with an introduction, with the motivation of how this project comes about. Here we go. And of course, I start with these automated driving levels that we have talked about before and has been talked about for many years in this area of research, especially level 2 and 3. Level 2, where the driver has to always monitor the system and the operation, and in level 3, where the driver can already disengage from driving to some extent and actually do other tasks at the time in the vehicle. So these two levels are becoming available in vehicles today. Level 2 has been around for a while. Level 3 is becoming available on some roads by some vehicles. And the problem from the human factor side has been discussed several times already, is how do you differentiate from a driver side between these modes of automated driving? I mean, it looks pretty much the same. The vehicle seems to steer, seems to brake, but the responsibility is very different between level 2 and level 3. And especially, and then if you go the next level, so this idea of the fragmentation of a trip as it's currently happens in automated vehicles that are on the market or will be on the market soon, is fragmented. So we have manual driving intermingled with level 2 driving, level 3 driving, maybe level 2 driving goes back and forth. And so on a trip, you will experience in the near future many types of automated driving levels. And the question is, well, how can we do this safely? How can we do this in a way that is acceptable from the user perspective? And this is really the idea behind the call that was really clearly stating we need solutions for this kind of problem. So this call started our project. We applied as a consortium of 16 partners to this call. It was running for 42 months. We started in December 2019, just before COVID was hitting. So we had our kickoff meeting before COVID, which was nice. But then COVID hit us, but we finished on time in May 2023 with the project, and I will tell you the main results and impact that we think we have achieved in the project. Our approach to solve this problem is, we call it holistic, and the term holistic is often used when we are in the human factors domain. Holistic, really, when we engage the human really in the operation, it very soon becomes holistic. But we had a very specific meaning with holistic that goes even beyond the human. So traditionally, when we focus automated driving efforts, we very much focus on the vehicle itself. But that often leads us to shifting those tasks that the automated driving vehicle cannot perform, shifting this to the human. And that causes some of the problems that we are trying to address in this project. So we have a very automated vehicle-centered view, and what we think is needed with holistic, we need to integrate in the development of solutions more the vehicle, the HCI, so the human-computer interactions, but also the road infrastructure, legal training, and the human. So all of this really should be considered, and this is what we set out with what we mean with holistic, and I will give you more concrete instantiations of what this meant in the project. So we investigated exactly such a holistic solution, and we tried to measure the results and showed the impact for that when we do that. So holistic, human-centered. Human, of course, is in the center. We look at the mobility needs for automated driving vehicles in the next 5 to 10 years. For this, we need a crystal ball, which in our case is our European visions of where does mobility move in terms of public transportation, which gets a more and more important role for sustainable transport, and where does automated vehicles stand in the near future. So we start with the mobility needs of humans for automated driving in the near future. Then, of course, the vehicle has a critical part. In-vehicle solutions, HCI solutions, driver monitoring solutions are investigated in the project. But then, and this is really the key for our holistic approach here, is we also integrated the road infrastructure, especially information about what is ahead of the automated driving vehicle, communicating this to the vehicle itself through sensors, through CITS messages, and in this way expanding the prediction horizon, the viewing horizon of a vehicle, what the vehicle knows, what's coming up, and in this way increasing the predictability and the availability also of the automated driving functions. So we think that all three of these aspects together give us much better answers than just some of the components of it. So this is then our HADRIAN, which stands for holistic approach, and the long text you have there. So we start with the human-centered vision. This is our crystal ball. How will automated driving be usable in the near future, in the next 5-10 years? There are many visions available, many ideas, roadmaps where the European Union, where Europe, where countries and cities want to go. We read many of these visions and extracted from these visions specific use cases. So it's a user-centered approach. We have personas involved. We identified 3 different personas. One, an elderly driver who wants to stay mobile with automated driving functions. We have a truck driver to increase the attractiveness of this very, the job as a truck driver is not as attractive anymore as it used to be. So how to increase the attractiveness of this job environment. And then somebody who wants to work in the vehicle, somebody who needs to be productive while being on a trip. So these 3 personas form the core extracted from these mobility visions. And then for this we created 12 mobility scenarios. These mobility scenarios were extracted for urban environments, suburban environments, rural environments, and also ride-sharing environments. So these 12 scenarios really are forming the backbone of the project, because it really gives us the goals, what are the mobility needs, and how can we address them with these different types of automated driving functions. So this was the start, and we present our results. So this was at the very beginning. Now this is at the end. Last year in May, we had our public event. We had our demonstrator vehicle, 2 demonstrator vehicles where we implemented the solutions, presented the results to the public, met 2 days and presented all the solutions on this. And you see some of the vehicles, also the road information infrastructure. We had a trailer in the back. And I will, in the following slides, just give you a short summary of some of the highlights. And the idea is to give you points of interest where you can find more information on this. So this is the idea of the next 2 slides, or 3 slides that I will present just on the results. Most of the research in the HADRIAN project, but not all, so in the end we come to the field demonstrations, but most of the research was conducted in driving simulators. We had overall 22 studies across Europe and Turkey with more than 800 human participants. And we described thoroughly all these studies that are available on this link, and you will have other links later on where you find them. But what did we do? So just some highlights. One is we looked at seat repositioning as one way to communicate a change of automation level to the driver. We found this to be very intuitive if you do it right, if you have the right angle. For example, we tried seat inclination, but seat inclination didn't work so well. So the seat angle of 15 degrees about was found to be a very effective way. If integrated with other solutions. You can't just turn the seat, of course, you need to integrate it with other display solutions, especially auditory alerts and so this is part of what we tried to also show, is how do you can use each of the single innovations, here seat rotation, into a comprehensive cockpit layout or a vehicle cabin layout. A second piece of we looked at were head-up displays. Head-up displays are becoming, of course, available more and more. It's a prime real estate for seeing information, getting information. We were interested in some of these large augmented reality type displays where you have information that actually overlays into the real environment and seems to really augment what you see out there. We didn't find, interestingly, so big benefits of having large head-up displays that have this integrated view. We found more head-up displays were highly appreciated information on head-up displays, especially the information you see there, speed limits, time to collision warnings, and navigation information. So we investigated what information was most beneficial that is as the minimum displayed on such head-up displays. We looked at different driver state-dependent haptic feedback, so haptic feedback, looking at different signals that can be communicated from the steering wheel, for example, a state change for a takeover request and so on. What haptic symbols are most intuitive to be perceived, to be used by our drivers? And lots of possibilities out there, from intensity, the shape of the signal, and just different ideas. It's almost infinite universe. So we looked at a lot of those, and we found some that clearly work better than others. And so we reported on those, and we used them then in follow-on simulations. What we also did was, beyond haptic displays, we also, and this is a use case you can think of an elderly driver, we called it the guarding angel assistant. So it's really a vehicle that has automated driving functionality, but uses this in the background, leaving the driver in manual driving mode. So an elderly person may not necessarily need to disengage from driving, but needs to be supported maybe in some situations to compensate cognitive, motoric, maybe some decrements in performance. And so there we developed this guarding angel adaptive force feedback on the steering wheel that adjusted to the level of the driver, giving strong force feedback, avoiding an obstacle when the driver was distracted, being less strong when the driver was attentive. So it was a driver state-dependent interventions in terms of the keeping a safe envelope of the vehicle. We looked at different ambient lighting solutions. You see new vehicles of today, they have a lot of ambient lights. And the question is, how can you use this in a way that is safe and really useful? We learned less is more in this case. So ambient lighting can be very helpful, but it should not be overused. So when we tried to use more than 2 colors, it was very complicated for our participants. We used only one color really for automated driving indication, for level indication, not 2 colors, but 1 color, and then another color for warnings that are kind of requiring immediate attention of the driver. So this is, again, the integration guidelines are really important to bring this into a cockpit together with other innovations. And finally, we looked also at sound designs. Soundscapes are becoming common features in vehicles of today. You hear door opening, you have these very cool sounds that are played, but do they have a safety impact? And the idea is soundscapes could provide, of course, location information through a spatial arrangement of what you hear. The danger may be over there, or it moves back, or from the right. We did so far not find, really couldn't confirm soundscapes to be highly effective, but we designed sound icons for different events combined with haptic icons or not. So these sound icons are also available on our website for use in other studies or for use in application in real vehicles. And then I come to one piece that we have so far talked mostly about, vehicle interactions with the human. Now we come about an innovation. We investigated this specifically on helping build the driver competences with vehicles. So, you know, as today, when you get into a new car, well, you have a handbook, maybe a PDF format or something you can download, but many drivers don't read these handbooks. So maybe this changes in the future, but sometimes they're also not written really for understanding. They're more for legal responsibility, that everything is written in there, and if the driver behaves incorrectly, then, you know, they can't sue the car company. But it's often, they're not very easy to read, and we found, and what often happens, drivers don't really read the manual. They take the car, drive out there, and learn by error, trial by error. And this is dangerous, of course. If you don't have the chance to learn really all the limitations of your automated driving system, it's a problem. What we did in this to address this, we developed a tutoring application that on one hand it explained in a multimedial format, so in videos and audio, the responsibilities, the tasks of the driver, the tasks of what the vehicle does, when it does it, how to engage, disengage, and so on. But even I think more important, and maybe the most important feature of this system was it was combined with the in-cabin driver monitoring system. So it was able to adjust to what it observed the driver to do. So a driver, and we heard this yesterday, when the driver was too quick in taking back control, because it was just a 2-3 second fast response after a takeover request, the system would afterwards explain to the driver, okay, good, but next time, please check the rear view mirror, look outside, and make some control your, learn to do this in a safe way. I mean, this would be in the initial tutoring already, but this would be adaptively giving feedback to drivers to that. We were a little concerned, well, would drivers really like that? But in fact, we first found that when we gave this dynamic feedback, so only the drivers who did not perform this takeover in a safe way, or at least timely in a safe way, only they would get the feedback, so it would not annoy them after a while again, so this was important. They changed their scanning behavior, so during the takeoff they looked much more outside of on the road itself, so they focused more where they should focus the road during the takeover itself. But also they gave us feedback that this helped them reduce ambiguity, because they received feedback of what the system, if they were doing something right? So this nagging noise, it was a very nice voice, so not really too nagging, but the voice would not come up when they did it right. So then okay, this works now, I do it right. So it was really nice to ambiguity reduction. This is what we learned in the simulator studies. Now let me go to the HADRIAN demonstration. So we brought them, and this was, I must say, very glad that this was a requirement in the call, that we had to not only do the research in our simulators, but actually bring them into the field and show how this works on actual vehicles, on test tracks, but also on open road environments. It was a big learning experience of bringing what it can relatively easily do in a simulator, but making this realistic enough in a real vehicle with a real automated driving functionality. So we had 3 demonstrations, one in Austria, in Spain, and in Turkey. And in the following slides, I will just briefly talk about the first one, the one that happened in Austria on an actual highway. You see the use cases that they addressed specifically. So I have the working in the cabin use case as main guide in this demonstration. So what we did is we implemented the innovations. I presented them before. You see them on the right upper screen. So here we integrate this in these cabin solutions in an actual vehicle and compared, and we actually had 2 versions of our vehicle. Our vehicle was in the standard configuration without these innovations. It had just automated driving with standard features, and then compared this with a configuration where it had all these features implemented. Now, what were the important features I've not talked about before? This vehicle we actually integrated with CITS messages with the roadside infrastructure, road information infrastructure. That means road closures were available to the automated driving vehicle before the vehicle would actually pick anything up through its radar and LiDAR sensors, right? So the idea here was the vehicle receives a message from the roadside and is able then to plan a transition, a controlled transition, giving 15 seconds or more during level 3 driving to the driver to take back control. So this was one, so we increased the predictability of level 3 driving through integration with the actual CITS infrastructure. Now, these messages are not new messages. We use messages that are available. The CITS infrastructure is available on the segments on this highway as of today. So they were actually for the last couple of years. So we use these existing messages. So what the integration was really is to take this in the vehicle, process them, and inform the driving functions as well as the driver about it. We also predicted the expected SA level 3 duration. So you can see here, on this display here, you see the road, parts of the road where level 3 driving would be available based on messages, different type of messages would inform the driver where level 3 driving seems possible today. It may change, right? But to constructions, other things, but they would be available. So predicted availability of the expected LA level 3 driving, and then also, and this is also new because in level 3 automation, automated driving level 2. At level 2, we don't have any warnings. The driver is supposed to monitor permanently anyway. So the driver, we gave 5-second time warning prior to level 2 disengagement to see what impact this would have. Yeah? Because drivers often don't do the monitoring they're supposed to do. So this is what we found. Overall, we found very clear, juicy benefits of the HADRIAN innovations. Safety, perceived joy of performing a non-driving related activity at the site when you were actually knowing how long you're going to stay at level 3 driving. Usefulness, assistance quality, and the display quality. But maybe, and this is the key message, and also in terms of impact, the most important three features were increasing the predictability of AD availability, so knowing the driver knew where to drive, how long to drive at level 3, the planability, being able to be at the beginning of the trip already knowing where this could be performed on the longer trip, what kind of activities they could perform. And then the third piece is the monitoring the driver and giving adaptive feedback when the driver was not performing as he or she should be doing. Yeah. So this was for us the biggest, I would say, takeaway, is that such integrated holistic solutions go way beyond what we had expected from separate solutions. Or just HCI solutions that happen just in the vehicle itself without actually expanding what is an automated driving vehicle. Yeah. So we have documented all our results. They are available on the website. We are also not only preparing, it is being published in April and June. Will be available a book about our lessons learned, about how we can shape automated driving to actually achieve societal mobility needs, where we put all of what we have learned and experienced into this book, where we can read everything that we did and what we learned. So my last slide, we have investigated a holistic approach to render AD useful for societal mobility needs. We understand relative contributions of what you can do. And for us, it's really key is this holistic approach of expanding what we think of solution just beyond the automated driving vehicle, going much larger and integrating, for example, road information infrastructure, making this really an integral part of what it represents an automated driving system. We find it is maybe difficult to do this in current ecostructures of ecosystems, how automated vehicles are developed. I think we need to bring, in an even greater extent, bringing together the different expertise, organizations, funding mechanisms, education system, recognition systems, from purely maybe more isolated, kind of specialty-driven systems to kind of more integrated systems. I think this is a challenge that we need to really make these promising solutions reality, is to go into creating these systems engineering landscapes that allow us to build these larger kind of systems versus the isolated systems that we are still currently very much investigating, I would say. So with this, thank you very much. And I think questions will come maybe later, or yeah. All right, thanks.
Thank you, Peter, for your very comprehensive presentation. I think from your project we can see really you have a series of catalog of different AD solutions which could help the driver in future automation level solutions between level 2 and level 3, which is really a difficult situation. And I think you also open a lot of questions for future implementation activities in the future. But we'll come back to that during the Q&A session after. I would like to introduce now the second speaker in our session this morning, with Silvia Chiesa from the NextPerception project. This is a project, in fact, which is financed by the Excel joint undertaking. So it's good also to see the synergies with different instruments within Horizon Europe. So Silvia is a PhD student, and she's now a researcher and project manager at RILab in Italy. She's also specialized in human-machine interaction and human factors. And she leads also the collaborative project spanning automotive, healthcare, and creative sectors, because the NextPerception project was a wide project. So she will focus today mostly on the automotive application. Your floor is yours.
Thank you for the presentation. Hi, everybody. I'm Silvia Chiesa, and now I'm going to present you the NextPerception project. Okay, just 2 words to present the overall project. NextPerception started in May 2020. Okay. And ended this September 2023. As already said, it's part of the Excel program, and there is a problem with the slide because it continue to change the slide without my etc. I'm not doing nothing. So again, the previous one. I'm not the project coordinator of NextPerception because it was coordinated by VTT. I'm sorry for this problem, I don't know why. The NextPerception project was composed by 43 partners from 7 different countries in Europe. The objective of this project is to develop a system for the monitoring and observation of the people in different contexts. The objectives can be summarized in the 3 different points: the development of smart sensors, develop a distributed intelligence system for the monitoring of people, and create a proactive behavior, so try to develop interface HMI to provide in real time a feedback regarding the state of the person. I said person, people, not driver, because in this project there are different use cases that focused on different aspects. The first use case was related to the health and the well-being. So in this use case, we created different sensors for the monitoring of elderly people, of person playing sports. For example, developing non-obtrusive sensors to monitor the safety of the person while sleeping. The second use case is related to the driver monitoring system, while the third use case focused on the monitoring of vehicles on intersection, and focused also on vulnerable users on the street. Now I'm going to present in more detail the second use case related to the driver monitoring system. In this use case, we focused on different aspects of the driver, as for example, emotion, physiological signals, distraction, attention. And in this use case, we created 2 different systems, driver monitoring system, that we implemented. The first one on a driving simulator, the second one on a real vehicle, and in particular on a car and on a truck, on a heavy-duty vehicle. So this is the architecture of the complete system implemented on the driving simulator. As you can see, the first modules, the first classifier we developed, it's the so-called joint driver vehicle emotional status classifier. In this case, thanks to a thermal camera and a wearable device, we collected information to understand the activation, the arousal of the driver. The second classifier collects information from a lateral camera and a frontal camera, and it's able to understand the distraction, the movement of the driver inside the vehicle. In particular, it focuses on the steering wheel and on the central display, and it is able to understand, for example, when the driver is using the smartphone. The third classifier is the emotion detection classifier, that it focuses on the facial expression of the driver. In this case, focusing on a different point on the face of the participant, of the people, it's able to understand the facial expression, so the emotion felt by the driver. The final classifier is the cognitive distraction classifier or visual distraction classifier. It focuses on the gaze of the driver and collect also data from the vehicle. Of course, finally, we collected the data from the driving simulator, as for example, the position of the vehicle in the street, the speed, etc. We collected all this information together in a synchronized way, and we calculated a so-called driver complex state that is a value that it's a value from 0 to 1 to understand if the driver is able to continue his task. And then we developed a decision support system that is the module deputed to take the final decision, that is to switch to the autopilot or send different kind of message on the cluster. Indeed, we developed different kind of HMI with different warning messages and information provided to the driver that reflects the distraction and the level of activation of the driver. So this system has been implemented in the driving simulator, while this architecture has been developed and implemented on real vehicles. In this case, we implemented radar and Pharos accelerometer inside the vehicle to collect physiological signals, and together with eye movement to define a sleepiness value of the driver. Moreover, thanks to the use of in-vehicle cameras, we focused on the head and gaze direction and position. Moreover, we also implemented LiDAR outside the vehicle, and we collected the data from the vehicle, as for example, speed, location, odometry, to create a value for the distraction of the driver. We tested these systems in Finland because the vehicle and the truck are from VTT and TTS. So we tested this system with expert driver on real street. While this is the procedure we run to test the system in the driving simulator. For example, we started, of course, with a baseline, so participants have just to drive in the driving simulator. Then we ask participants to make a cognitive task, that is a memory task. Then we asked participants to execute a task using their phone to validate the visual distraction. And then we ask participants to drive listening different kind of music in order to elicit different kind of emotions. And finally, we try to combine all these different distractions. This is just an example of the scenarios and the task we ask to the different participants. In this case, as for example, you can see the driver is using the smartphone. So this is the, let's say, visual distraction. This is an example of the scenario where participants drove. We tested both on city scenario and on a highway scenario. And finally, I just reported this MQTT screen that reports the different messages that the classifier and the different modules are exchanging. So we obtained good results related both to the technical point of view, to the system, and from the user point of view. Regarding the technical KPI, we obtained a synchronized, we have been able to synchronize all the different modules, and we have been able to understand the real distraction, the real status of the driver. As already said, we test the system with a lot of users. Generally, they report a good opinion, good acceptance of the system and the monitoring. We investigated in particular the messages and the output provided by the HMI, the interface, and they reported a good acceptability, a good usability of the cluster. So this is the main results obtained in this project. Of course, we can improve the systems developed in the project, but generally we obtain important results that can be implemented on a real vehicle. Even because we have to consider that the driver monitoring systems will be mandatory in the next vehicle that have to be produced. So this is the general results obtained. The project, as already said, ended in September 2023, but we will have a follow-up of the project because we are going to start with the same partners, another project named Distremuse. So maybe you will see the next step of the project. Thank you.
Thank you, Silvia, for your indeed very nice presentation. I like your presentation, the view from the smart perception sensors to be applied to the automotive sector, also because you look at that for not only the driver, but also the passengers and also for the outside people, the vulnerable road users. We'll now come to the Q&A session. My colleague Magnus will manage this session.
Yes, thank you very much. And again, different aspects, but also things we, in one way, heard before, in one sense, but looking at the technologies that are needed, looking at the implementations, looking at the take-up, and so on. So it fits very, very nicely, I think, into the 3 projects we had before the break as well. So, questions? Natasha? And a runner. You get a lot of exercise these days, Marcina.
If you fit that. Thank you. Really interesting 2 presentations. All driver hot monitoring is definitely the hot topic. So to Silvia, I was just wondering if you can say a little bit about your cognitive distraction task and how you separate the visual manual element of that from the visual task.
Okay. Does it work? Okay. Yeah, we with the cognitive classifier, we try to understand if we will be able to separate only the cognitive distraction with the visual distraction. For this reason, we tested 2 different conditions. The first one only cognitive, that is the one with the memory task, and the other one only, well, actually was both visual and cognitive distraction, because of course we cannot separate, I mean, the cognitive distraction. For example, we asked participants to use the smartphone and text messages. So in this case, of course, it's cognitive because they have to memorize the words they have to write on the smartphone. So these conditions are the conditions tested in the last test of the project. Of course, during the 3 years, we ran different tests to validate the specific classifier. If I will remember, in other tests, we focused even just on the visual distraction. So we asked participants to move, to take an object from one side and put the object on another place. So that was only a visual distraction condition.
Sorry, just to be clear, so what I guess I'm trying to get at is when they're not visually distracted, and they've got their hands on the steering wheel or whatever, but they are cognitively distracted. Obviously it's difficult, but I don't think you looked at that, right? So for example, if they're doing a hands-free phone conversation, so their eyes on the road, their hands are on the steering wheel, then it's what I would call a pure cognitive distraction, and whether or not we can classify that. But I don't think you looked at that at the moment, right? Okay, thank you.
No. Yeah, it's probably similar to the emotion condition, where they just listened a music, but no, we didn't test it. But good point, actually. Yeah.
Good, thank you. So, who's next?
Thank you. Guus Arts, Trucks. I have 2 questions, one for both of you in regard to the acceptance of drivers being monitored. You can answer that one. And the other one is, what would be the behavior of the driver when he finds out that he has an autopilot as a fallback system, and how would that change his behavior as a driver who should have his hands on the wheel and eyes on the road? That's what I understood from Sylvia's presentation, that's the case.
Sorry, I didn't catch the question, sorry.
The second question was about, you mentioned in your presentation that that an autopilot function be available to the driver when he's not paying sufficient attention to the road?
Yeah.
How would that influence the behavior of the driver when he finds out that he has that fallback in place?
Okay. When the level of distraction was too high, of course we started before with different messages on the cluster to ask the driver to maintain the focus on the street. But we try to maintain the distraction of the driver, and when the distraction was too high, the vehicle switched to the autopilot. Of course, we provided different messages to different the HMI changed from the manual one to the autonomous one. Of course, it was just on the driving simulator condition, and yeah, we provided, there was a sort of countdown when that informed driver the switching to the autopilot.
Okay, but have you continued testing, and did you find out what that would
No, the simulator
on the behavior of the driver?
The simulator ended after the autopilot, and we just asked summarize, ask to the participant to answer to different questions, to answer regarding how they where we're feeling the switch to the autopilot, to the switching mode. But I don't remember particular negative opinion regarding this aspect.
Okay, so maybe a topic for a follow-up.
Okay, yes, sure.
Thank you.
I think maybe just you had the first question was about acceptance of driver monitoring systems, and you know, in our studies we have participants who are coming in for these studies, and so their acceptance is relatively high, but I wouldn't say that it is reflective of the population out there. I think it's a very good point. Who wants to be monitored by a system, especially when it's not clear where the information goes, where it's located, what is done with it? So I think these are often things that need to be clarified. I mean, I think that a clear safety benefit is certainly one aspect to convince, but I think answering these questions and communicating them to the user would be a very, very important prerequisite for widespread acceptance. Yeah.
Okay, clear. Thank you very much.
Yes, and just behind you.
Waited for you to be the real. Jack Kreuzinger, Toyota Motor Europe. I have a question to Peter, and maybe I can introduce. We have driver monitoring system now in general safety regulations, so people will have to cope with it anyway. So acceptance is maybe not the question anymore. But
just go with it.
So I have a question actually to Peter. You have introduced a couple of very interesting ideas about how to communicate with the driver about the status of the car, of the environment, readiness to take over, when it is time to hand over. Some of that by a tutoring system, some of that with additional information. When I see that, I am getting a little bit worried that we are trying to remove unnecessary information. At the same time, we are putting on top more. Did you have in your project also some evaluation how people actually like it, how they perceive it, how do they react to it?
So I think it's a very important piece not to overload the driver with information, so absolutely, and too much is certainly not good. But I think the introduction of this information needs to be providing a benefit, right? So if we provide information about the availability, for example, of where level 3 driving on a planned trip is available or not, and there is no relation to what the driver wants to do with it, it's pretty perceived useless, unnecessary information. But in the context of a use case where the driver wants to work on the way to the destination, this becomes useful information. So it really depends on the use situation, and what information to provide really depends on very specifically the user and for what purpose the vehicle is used. So I would say the answer is really this is the tailoring of the vehicle information to the specific user and not providing that information that is perceived as annoying or not necessary. I hope that answers your question.
Did you study that in the project?
Yes, we did study that in the project, especially, you know, the annoyance. We thought, for example, providing feedback about the driver taking back control that could be annoyed and could be perceived as you don't tell me what to do. And this is what we expected. But when it was paired with, you know, when the feedback is given in a way that it's not offensive, but you know, tries to help a proactive, a good behavior, it's much more acceptable in this way. And so this is what we found. It was accepted when you put it in the right context, in the right way. So.
Yes, we have time for one or more, or one or two more questions, I think. I can pose one while you're thinking. Yeah, please.
Thank you very much, George Charles from CINEA. So, Peter, since your project is over, I think it would be always interesting for us to know, of course, we have seen the results, but it's important to know actually what it didn't work well. So about the lesson learned. You mentioned that actually you are now, which is in preparation, a book. So if you can give us a flavor of this lesson learned.
Well, thank you very much. This is a very nice question. What I would really wish is a more, I would say, integrated research support. So meaning, we can bring together, for example, we have defined use cases that are really interested for municipalities and for the EU in general to go forward and really provide them as an input before you go into research. That is helpful because then you can actually focus, you can focus the partners more, not on what each partner wants just to do by themselves, but allows some converging onto real use cases that are, in the public interest in societal needs. This would very much help. Otherwise, what we see often is use cases are sometimes use cases are, technical excuses to demonstrate and build technical systems that are just exactly working for this one use case. And I think there were questions early on that. But if we have catalogs of use cases, a vision where the European mobility wants to move to, what are the applications for automated driving that really get a lot of funding, not only for 1 or 2 or 4 years, but for 10 years, 15 years, I think it will really help to converge the technical solutions, and it will help us to establish these larger solutions, not just the silos of solutions, but creating these larger solutions. So I would wish for that, and we try to express this also in this book that we mentioned, more of these use cases that really shape where do we want to go with automated driving from a societal level. That would help, I think.
Okay, good. Thank you. We're about to finish. I would just like to direct at you, Silvia. I think it's first of all, it's a very good example, as you were saying, Patrick, how the Excel program can sort of fit into the needs that we see within the Horizon Europe, and I think we could do more on that. I'm also very curious about the other use cases that you have. I know that you're focusing now on this specific one, but especially the one on the health, because we've seen some other activities as well where you can reuse the knowledge and understanding and algorithms and so on, and in detecting and in that specific case certain illnesses, for instance, that you can have as a driver as well. Do you want to comment anything on sort of the commonalities between the use cases?
Yeah. No, absolutely. It's a very good point. And actually, inside the project, we run different activities of cross-pollination between use case and pilot inside the use case. Because, for example, in the first use case related to the health and well-being, some pilots focus on elderly people inside the house, other are more related to the sport, but they try to exchange the systems and the sensors among the different use cases. So it's a very good point, and in a project like this, where there are a lot of partners from with different expertise, it's useful to learn a lot from them. Yeah.
Good. Thank you very much, and I will put you in contact with some additional people. So thank you very much. Thank you very much to the speakers.